All right, so today we're going to begin our final topic of the semester, which is on finding volumes of different shapes. Now, for volumes, we're going to use integration to do that. So you may already know, and you probably already know that you could use integrals to find areas of the area under a curve. But today we're going to see that we could also use integrals to compute volumes as well. Normally we would have talked about this earlier in the semester, but due to scheduling and the way things kind of lined up, it actually was more convenient to have this be at the end. Despite that, the integrals that we're going to be doing typically aren't going to be too difficult to do. Most of the time, you just end up doing the power rule or something like along that level. So these are almost all Calc 1 integrals. So fortunately, the integrals won't be too bad to do. It's setting them up that could be a little bit difficult, kind of like the area integrals from polar coordinates. So let's go ahead and get started and talk about how we're going to find volumes. So for the first example for volume, I want to pick a shape that we already know the formula for volume for. So we can kind of check this new technique to make sure that it works against well-known formulas. So what I'm going to do is I'm going to try to find the volume of a cone. And if you go on the internet and look this up, the volume of a cone is 1/3 pi r squared h, where r is this radius right here, and then h is this height right here. So for example, if we have a height of 5 and a radius of 10, so I guess it definitely wouldn't be that cone, the radius would be way longer, then we would put that into here, and we'd have 10 squared, which is 100, and then times h, which is 5. So if we multiply all that out, it's going to be 500 pi divided by 3. So that would be the volume of a cone with these dimensions right here. Now what we're going to do is we're going to find this volume, but in a different way. And then at least we know we can check our answer once we're finished with it. So first of all, I'm going to try to draw this cone maybe a little bit more to scale. There's our height. Here's our radius. And then it goes the same way the other way. And then we have a circle like that. So here's our cone. It's very kind of long and flat. Now what I'm going to do is I'm first going to approximate the volume of this cone by stacking two cylinders together. So it'd be kind of almost like a two-tiered cake. So what's going to happen is I'm going to cut this in half, and my first cylinder is going to be half the height of the cone. If you can see this, I just drew another circle to represent this bottom cylinder right here. It's going to be very big. So the height of this cylinder will be half the height of the cone, which is 2.5, and the radius, since we went all the way to the bottom here, the radius for that will be 10. And then what I'm going to do to get this top bit right here, if I go halfway up and draw a line right there, then I can have another little cylinder on top of the big one right there. So this cylinder will go all the way to the top of this cone. So this will also have a height of 2.5 since we carved it up into two cylinders. But this time, since we're starting halfway up the cylinder, our radius is going to be half of what it is at the base. So it's going to be of radius 5. So what we could do is we could figure out the volume of cylinder 1, which that's going to be pi. R squared will be 10 squared, and then h, which is 2.5. And then we'll have cylinder 2, which is pi, and then the radius now is only 5, and then we multiply by 2.5 there. Now this is going to give us some kind of weird decimal, but I already know that this is actually going to be an overestimate for how big this cone is going to be, because you can kind of see that these cylinders sort of go over the edge of the cone. They include the entire cone, but then they accidentally kind of go over the slanted side. So whatever this number is, if you add these two things together, this is going to be bigger than the volume of a cylinder of a cone. Now you probably can guess what we're going to do next. We can get a better approximation for this volume by having more cylinders. So the more cylinders we have, the more finely it'll match up to this cone, and we'll have less and less volume kind of going over the edges there. And I bet you can guess what happens next as well. when we send the number of cylinders to infinity, we make them infinitely thin, then we'll get the exact volume of this cone. So that's what we're going to do next. And whenever we do that process, that's going to create an integral. So that's why we're going to be doing integrals for this part. Now, the thing is, we need to know exactly what integral we're going to set up. So let's draw this cone again. This time I'm just going to kind of look at it from the side. It's like a big triangle here. So let's say that we go a certain amount down from the top, which I'll call h, and then we have a certain radius at that height h. And let's pretend that we have one of these really thin cylinders here. So there's the top of my cylinder, and then here's the bottom part of my cylinder right there. So it's like a very thin kind of disc. And so it has height from the top, h, and then radius, r. Now, notice that we end up getting a triangle here. So we have this triangle made of h, r, and then part of the hypotenuse there. But then we could also make a triangle that goes over the whole cone. So we have, this is our one leg, this is another, and then the entire hypotenuse right there. And we remember, we know the dimensions of this. It's going to be 5 tall and then 10 long, like this. Now, you may notice a relationship between these triangles. These triangles look the same, except one is just bigger than the other. So these are similar triangles. What that means is we can actually make a ratio between their side lengths. So h over r, so the vertical over horizontal side, is going to be 5 over 10, which it is for the bigger triangle right there. So what I'm going to do is I'm going to simplify this to be 1/2. And then I'm going to multiply both sides by r. So whatever h is, it's going to be 1/2 r. Or in other words, 2 times h is going to be an r. So whenever we see an r, we can replace it with a 2h. Okay, well, why did I bother doing all of that stuff? What's the volume of each one of these little cylinders right here? Well, remember, the volume of a cylinder, so VC, is pi r squared times h. But this time, the height of the cylinder is going to be really, really tiny. And anytime we want to symbolize it being really small, remember, we say it's going to be d, and then whatever variable it is in the direction, that's going to be a very small change in. So our volume for our cylinder is going to be pi r squared, and then we have dh, because its height is going to be very tiny. And then what we would do is we would integrate, we would add up all of the volumes of these tiny little cylinders, pi r squared dh in our integral. The smallest h can be is 0 distance from the top, and the biggest h can be is the maximum height of the pyramid, which is going to be 0 to 5 right there. So if we do this integral, then we'll get the volume of our cone. But the problem is we can't do this integral yet because we have r as a variable right there, but we're doing the integral with respect to h. So this is where this equation is going to come in handy. We're going to convert our r's over to h's. This is the integral from 0 to 5. We have pi, and I'm going to have 2h in there and square that. So when all is said and done, all I need to do is do the integral from 0 to 5. I'm going to have a 4 pi on the outside of h squared dh. All right, and as I promised earlier, these integrals won't be too bad. And this one's just going to be doing a power rule. So we raise the power to 3, and then we divide by 3. We have 4 pi over 3h cubed from 0 to 5. Now let's remember our answer from earlier. So remember, whatever we get for this, it needs to be 500 pi over 3 in some way. We got that from just the general area or volume formula for a cone. So if I plug 5 into here, I do 5 cubed, which is 5, 25, and then 125. If we do 125 times 4, thankfully that'll end up being 500. And we have pi over 3. If I plug 0 into here, then, well, 0 will just give us 0. So we end up getting that our volume really is 500 pi over 3 for this. So this is an alternative way for computing volume. Now you may look at this and be like, okay, well, I found this formula online in like 2 seconds by Googling it, and I just plugged in the numbers and they gave me this. Why would I go through this entire process of creating an integral just to get the same answer? Well, for common shapes like spheres, boxes, cones, pyramids, etc., yeah, I definitely encourage you to just look it up online rather than going through this whole process. But sometimes we'll need to find the volume of shapes that are rather irregular. So things that are not common enough to have a nice kind of formula you could just look up. And so by practicing this on familiar shapes, we can end up becoming skilled enough at it to do it on shapes that don't have a common formula. That's actually going to be my next example. Let's take a look at some kind of a shape that doesn't have something that we can just look up to get its volume. So I'm going to start by drawing this parabola. Y is 1 minus x squared. And I'm going to draw that for x in between -1 to 1. So if I draw this, let's see. Here's my parabola. Kind of looks like this. It's going to go down because I have a negative right there. And then the point where it intersects the axis is going to be -1 here and 1 there. Okay, so there's our parabola, but that's a 2D shape. How are we going to get a volume from this? What I want to do is I want to find the volume with the parabola as a base. So that means that the bottom of whatever our 3D shape is going to be this parabola right here. With a parabola as a base and with cross sections perpendicular to the x-axis being squares. Okay, so that's kind of a mouthful, so let's go over what this means. So this is going to be the bottom shape right here, but remember, this is just a flat 2D shape. This isn't 3D yet. The way we're going to make it 3D is we're going to have cross sections perpendicular to the x-axis that are squares. We have 3 things to digest here. We need to talk about what cross sections are, what it means to be perpendicular to the x-axis, and then they're going to be squares. So a cross section you could think of as almost like a slice of our 3-dimensional shape. So, and those slices will be perpendicular to the x-axis, meaning that they're going to be going this way. So remember in the last problem, we had a really thin kind of cylinders, and that went in the h direction. Whatever variable they specify here, if it's perpendicular to that variable, our very small change is going to be in that direction. So whenever we're drawing our little shapes, they're going to have a very thin x component. So we're going to write that as dx, and that will be the thickness of all these shapes we're going to draw. Okay, so that's what perpendicular to the x-axis is. And then squares, what are the shapes? Well, they're just going to be squares with some tiny amount of thickness. So they're going to be very thin boxes. Now there's squares, right? So they have one leg of the square being in this direction, y, and then it's a 3D shape, right? So it's going to kind of pop out of the page a little bit. I'll try to draw that to the best of my ability. So imagine that this is kind of popping out of the board here, and they have to be squares, right? So if this bottom leg is y, then this leg has got to be y as well. So the volume of each of these chunks, I'll call it VP for the volume of a piece, is going to be y times y, and then times this dx thickness. So it's y squared dx. And just like before in the previous problem, if I want to get the volume of the entire shape, all I need to do is integrate from my first x value, -1, to my last x value, and then I throw in all of these volumes. But as what happened last time, we see we have 2 different variables here. So we have a y squared here and dx there. We just need to convert these y's to x's. And thankfully, we don't need to do similar triangles or anything like that to get that relationship. That relationship is already given to us with this parabola. Whenever I see a y, I can replace it with 1 minus x squared. So this is going to be the integral that I'm going to do right here. So now I have everything with x's in it, so now I can do the integral. And just like before, and as I promised earlier, these integrals rarely end up being too difficult. And this is just going to be another sort of power rule problem. But before we do that, I want to actually make this integral a little bit nicer. So this integral will be the same thing as the integral from 0 to 1 of 2 times this. And why is that true? Well, if we look at our parabola again, notice that we're making these sort of boxes over on this side. They kind of start at 0 and get bigger and bigger and bigger. And then we have exactly the same size boxes just going in a different direction over there. So whatever our volume is on this side of the y-axis is going to be the same as it is over here. So kind of like we use symmetry when we're figuring out polar areas, we could also use symmetry when we're figuring out these volumes. So rather than doing -1 to 1 like I did here, I'm just going to do the 2 times the integral from 0 to 1. And both of those integrals are fine. There's really nothing wrong with doing this one right here. It's just that this one might be easier because it has 0 as a bound. All right, well, in order to do this, I need to FOIL out this inside. So I get 1 minus 2x squared plus x to the 4th. And then I'm going to integrate by the power rule. All right, so I have x minus 2/3 x cubed plus x to the 5th over 5. And that's from 0 to 1. And then all we need to do now is just plug in 1 for all of our x's. So this will be 2 times 1 minus 2/3 plus 1/5 right there. And then when I plug in 0, all of those would just be 0. So if you like simplifying fractions, you could do that at home and figure out exactly the fraction that says whatever this number is will be the volume of this kind of wedge-shaped thing right here, where all these cross sections are squares, but they're going along this parabola right there. All right, well, that about does it for today's examples, and next time we'll learn about how to find volumes of shapes by taking a two-dimensional shape like this parabola and then spinning it around an axis. So that'll be next class. As always, let me know if you have any questions and I can help you out.